What specific problem does the proposed method aim to solve regarding LLMs and their understanding of language structure, particularly with respect to low-resource languages?
The proposed method aims to solve the problem of evaluating LLM's reasoning capacity regarding entirely novel languages, particularly to address concerns that LLMs may only understand linguistic structures similar to those seen in their training data. By defining a large, exhaustive space of languages and sampling random languages from this space, the method eliminates the possibility of dataset leakage and biases towards canonical languages. This approach is particularly relevant for low-resource languages, where LLMs tend to underperform compared to higher-resource languages. The experimental results indicate that contemporary LLMs struggle with basic language pattern recognition tasks, underperforming even against simple, parameter-free n-gram models. Ultimately, this method seeks to provide a benchmark for assessing LLM's ability to generalize to novel language reasoning tasks, which is crucial for understanding their true language comprehension capabilities.
How does the proposed method work? Illustrate the methodology step by step, especially the sampling of languages and the construction of the benchmark.
The proposed method for evaluating LLMs on language reasoning tasks involves several key steps. First, a large, exhaustive, and parsimoniously defined space of languages is established, representing all languages of a certain difficulty level, specifically focusing on Type 3 languages recognized by 3-state DFAs. Next, random languages are sampled from this defined space to ensure that there is no bias towards canonical languages that might share structures with those in the training dataset. For the evaluation, the methodology includes generating test cases by sampling a DFA, creating 30 example sequences of length 10 that the DFA accepts, and then sampling a distinct prefix of length 5 that is not a prefix of any of the example sequences. Finally, the task is to determine a valid completion of this prefix that the DFA would accept, and the models are evaluated based on their ability to predict these completions accurately. This systematic approach allows for a robust assessment of LLM's reasoning capabilities without the influence of prior training data.
Can you provide a simple yet illustrative example of how the sequence completion task is structured? Walk through the example of a DFA and how the model is expected to generate the valid completion.
In the sequence completion task, a model is presented with a deterministic finite automaton, DFA, that recognizes a specific language, along with a set of example sequences that the DFA accepts. For instance, if we sample a DFA that accepts binary strings with an even number of ones, the model is given 30 example sequences of length 10 that this DFA accepts. The task then requires the model to complete a distinct prefix of length 5 that is not part of any of the example sequences, ensuring that there exists a valid completion that the DFA would accept. The model must predict a completion of this prefix, which can be between 1 and 5 characters long, such that the entire sequence formed, the prefix plus the completion, is accepted by the DFA. The model's performance is evaluated based on whether its predicted completion results in a valid string in the language recognized by the DFA.
What are the practical benefits of using the proposed benchmark method over traditional evaluation methods for LLMs?
The proposed benchmark method offers several practical benefits over traditional evaluation methods for LLMs. Firstly, it ensures that the evaluation is conducted on wholly novel languages, which eliminates the risk of dataset leakage and biases that may arise from overlapping syntax or concepts with training data. This approach allows for a more accurate assessment of an LLM's reasoning capacity regarding language structure, as it tests the model's ability to generalize to entirely unfamiliar languages. Additionally, by focusing on languages recognized by 3-state DFAs, the benchmark targets a low but non-trivial difficulty level, providing a clear framework for evaluating language reasoning abilities. Experimental results indicate that this method reveals LLM's limitations in language pattern recognition, as they underperform compared to simpler parameter-free n-gram models, thus highlighting the need for further development in LLM capabilities.
How was the proposed method validated or tested? Discuss the experimental design, datasets used, and performance metrics in detail.
The proposed method was validated through a series of experiments involving a benchmark designed to evaluate LLMs on language reasoning tasks using three-state DFAs, which represent the simplest non-trivial languages. The experimental design involved sampling 1,000 distinct DFAs for the sequence completion task and 30 DFAs for the transducer task, ensuring that the tasks were disjoint from any training data the models had previously encountered. Performance metrics included binary prediction scores for the sequence completion task, where the accuracy was averaged over several sampled DFAs, and the transducer task, where the accuracy was compared against baseline models such as n-gram heuristics. The results indicated that LLMs consistently underperformed compared to these simple baselines, with specific prompting strategies yielding inconsistent results across different models. Overall, the experiments demonstrated that LLMs struggled with pattern recognition in unfamiliar language structures, as evidenced by their lower accuracy compared to the baseline models.
What specific results were achieved with this benchmark when evaluated on contemporary LLMs, and how do these results compare to the performance of simpler models such as n-gram models?
The evaluation of contemporary LLMs using the proposed benchmark revealed that they underperformed compared to simple, parameter-free n-gram models, even on the simplest languages recognized by three-state DFAs. Specifically, LLMs struggled to complete tasks that were nearly fully determined, achieving lower accuracy than the n-gram heuristics, which consistently outperformed them. For instance, in the sequence completion task, the n-gram models demonstrated a higher success rate, while LLMs showed inconsistent results across different prompting strategies. In the transducer task, all LLMs similarly failed to match the performance of a 4-gram model, indicating their inability to detect patterns from unfamiliar sources. Overall, these results suggest that LLMs function more as ensemble models over familiar tasks rather than exhibiting robust generalization capabilities to entirely novel language reasoning tasks.